I'll start by introducing John. So it's a great pleasure to have John Tamir giving us a presentation today in the ML+X seminar series. John is an assistant professor who recently joined us in the EC department at UT Austin. He received his PhD from UC Berkeley, and his work has been on computational medical imaging, signal processing, and machine learning. He has been doing very interesting work with on the foundations and also on enabling real clinical adoption. And he is a developer of the open source BART toolbox for computational MRI. So John, you have the floor.
All right, thanks, Alex. And thanks everyone for the invitation and taking the time out of your day to join. I hope you don't mind that I changed the title. I thought it was a little bit too complicated. So I'll be talking about computational MRI with some deep learning. All right, let's get started. So I first wanted to acknowledge all of the people who do the real work. So I'm really fortunate to work with a number of really talented students. And our group is called the Computational Sensing and Imaging Lab. And our goal is to jointly design imaging and sensing systems with computational algorithms, with the software, with a particular focus on MRI. And with that in mind, we work with clinicians to translate these techniques to the hospital. So what is computational MRI? Okay, computational MRI is the idea of using computation to jointly design the acquisition, the reconstruction, and the analysis. So we take the imaging system, we pair it with heavy computation, and then we redesign the way the data are acquired, and then what we do with that data, how it's reconstructed. And we use prior knowledge, in particular, what we're actually imaging, in order to inform the design of the acquisition and the reconstruction. But we don't just use the prior knowledge of who we're scanning at this instance. We also use the combined prior knowledge of all of the previous scans that we have. And we combine this with the imaging physics. So we want to take advantage of knowledge of how the system works when we use the prior knowledge to design these systems. And the ultimate goal in this space is really to combine all of the different components of the diagnostic imaging chain. So that starts even before we collect the data and design a smart acquisition, a smart reconstruction, a smart analysis, and then a smart reporting. And we want to do this all in a joint manner to get the most out of the information that we have. And so there's a role for machine learning to play in all of these different steps, while still keeping in mind that we want to also take advantage of the knowledge we have in the system. And for the time being, I've spent most of my effort focusing on the acquisition and the reconstruction, although I think it's really important to emphasize that there's a lot of space still that can be done to combine these different stages of the pipeline. By the way, if there's any questions, feel free to unmute and just ask. Be happy to answer as they go. Okay, so let's take a step back and let's talk about medical imaging. So this is what medical imaging looked like before 1895. This is a painting by Rembrandt. And really, the only way to see into the body was to cut. So pretty invasive. And something quite remarkable happened in 1895. This is medical imaging at that time, and this is an image taken by Röntgen, and this is the very first X-ray of a human subject, a living human subject taken. And this was Röntgen's wife. You can see the wedding ring on her hand. Very unfortunate, though, that at the time, there was little understanding of the effects of ionizing radiation. So these experiments were done on human subjects before really the safety standards kicked in. Okay, but things have progressed quite a bit since then, and this is what medical imaging can provide for us today. So this is an example of a magnetic resonance imaging scan of a 12-month-old baby. And this is courtesy of Stanford, Joseph Chang. And what we're seeing is this really high resolution, almost 1 millimeter isotropic resolution of a baby's beating heart. And as the heart beats, we also see these traces, these colors of the speed of the blood flow. And so it is quite remarkable what we can do non-invasively now with medical imaging. And as a result, this has led to rapid and accurate diagnoses. It's reduced the need for exploratory surgeries. It's led to better treatment outcomes and reduced healthcare costs. But there's still a number of open challenges. In particular, we want to do fast imaging. So MRI scans, even though it's non-invasive and doesn't cause ionizing radiation, it's order of magnitude slower compared to, for instance, CT. CT, you get an image in roughly seconds, whereas an MRI can take minutes to tens of minutes to even hours. We also still care about safe imaging. So even though MRI is non-ionizing, oftentimes with pediatric patients, we still have to sedate them and use anesthesia. And anesthesia is not that safe if it's being something that's done routinely for sick kids. And finally, we want to work on affordable imaging. Right now, MRI is very expensive, it requires big machines, and they're often inaccessible as a result. And so there's still a lot of room to improve in this imaging, computational imaging paradigm. So what is an imaging system? Well, an imaging system consists of an energy source that emits something, passes through the subject, and then an energy detector. And in the case of MRI, we're using magnetic field gradients to collect the data in the sequential process. And once we've collected the data, we use the imaging system knowledge, the algorithms, to invert that and turn it into an image. And the MRI system is just the coolest embedded system you could possibly work with. It involves so many facets of engineering, including electromagnetics, designing the magnet, RF and wireless design, DSP, digital signal processing, optimization, and many other components, including this little blob here, machine learning. But not only is MR does it cover engineering, it also covers many other areas of science, including chemistry, statistics, physics, medicine, psychology. So it's really a great opportunity to work with a diverse set of people with different expertises to try to improve things on different fronts. Now, how is the MR signal formed? Well, it's all about hydrogen. So when we image a person and we put them in the scanner, we're basically imaging their hydrogen spins, these atoms that have a spin angular momentum. And when we place them in a magnetic field, and so here's my magnetic field, 3 Tesla, then these spins will align with the main magnetic field, a small ratio of them will. And so here we have a magnetic field and the spins align with them. And now what we do is we interrogate the spin with RF energy. We emit a radio frequency pulse, and this causes the spin system to be perturbed. And when we place a receive coil near that spin, we will pick up a signal. And that signal will be related to the amount of spins in the position of the body and the various properties of that spin. When we turn off the RF pulse, things go back to normal and we can start the experiment again. And so we can abstract away these different spins and think of it as a spin distribution in 3D space, where at every position, we have a distribution of spins that are aligned with the main magnetic field. And we can think of the MRI system as this dynamical system, where in every position in the body, we have these spins and we have a particular spin distribution. And so we can call this spin magnetization the particular spin state at a particular time t. That's a function of both position, as well as intrinsic tissue parameters, intrinsic physical parameters of that particular spin. Now we have control over the pulse sequence. We decide what kind of acquisition to perform, and that's going to perturb the spin distribution and cause it to evolve. And so long as we know the spin dynamics, we can track how the spin will evolve over time. And we can carefully design these in order to get a particular type of image contrast. And so we can think of these different acquisition parameters as knobs that we have to tune. And as we change the parameters of the sequence, that causes the underlying spin distribution to change, which will cause the image contrast to change as well. And so by manipulating the sequence, we can manipulate the contrast, and we'll get different kinds of contrast that are used for different types of clinical decision-making. So that's how the acquisition, the signal acquisition is done. But then we also have to collect the data itself. And MRI has this really nice formulation in the frequency domain where we can say that the signal is the Fourier transform of the image that we're acquiring plus noise. And so, for example, we have an image X. It goes through a spatial Fourier transform into the measurement domain, which we call K-space. And then that's sampled at particular K-space locations to give us our measurements Y. And it's important to note that in MR, everything is complex valued. So in addition, we're working with magnitude and phase data. And as we collect the frequency samples, we fill in K-space, which gives us more information about the image. And every sample gives us some global information. And as we fill it up, we get higher and higher resolution, and we get a high diagnostic quality image. Now, the problem with this, if we want to collect data, is that it takes time. And the scan time in MR is proportional to the number of measurements that we take. It takes on the order of milliseconds to seconds to collect a sample. And so then the entire scan can take minutes to tens of minutes. Now, if we want to scan faster, we could just collect less data. But if we collect less data, for example, by not collecting all of the K-space measurements, then we'll have some kind of artifact in the image. And in particular, if we collect it in this randomized fashion, then we'll get this incoherent aliasing that looks like noise. And so undersampling causes artifacts, and the goal of the image reconstruction is to recover the image and remove these artifacts so that we can get a faster scan, but with the same quality image. Now, another thing I want to mention is that in MR, we're not collecting just one measurement, we're actually collecting channels of measurements. And so the data that we receive is from multiple coils. So we can place multiple coils around the anatomy, and each one is sensitive to a particular region in the body. So for example, this coil, which is sensitive to the back of the head, will pick up more signal from the back. And this one, which is on the right side, will pick up more signal near the front right. And these coils have a particular spatial sensitivity. And so we can model this as our image that has uniform sensitivity multiplied by the coil sensitivity profiles of each of these coils, and that gives us the coil images. Now, we still need to sample those coil images, and so the model is that we have a particular sampling pattern that's going to sample each of these different K-space data sets with the same sampling pattern. And so then we get this multi-channel data where each of these channels represents the image passed through this coil sensitivity and sampled. And we can pose this as image reconstruction as an inverse problem, where we have a particular objective function that consists of a data consistency term. We want our measurements and our image estimate to be consistent with each other. And then we add regularization. And the reason for the regularization is because in general, the problem is ill-posed. We have fewer measurements than we have unknown coefficients to resolve. And so the secret sauce is in this reconstruction algorithm for how to make the problem well-posed. And in the before time, people would regularize with handcrafted models. And in the case of MR, the two most common were wavelet sparsity, where we represent the image in the wavelet domain and recognize that it has a small number of non-zero coefficients, or using total variation, which penalizes the finite differences in essentially the derivative. And this is really useful for dynamic imaging, where the dynamics are changing smoothly or almost constant over most of the location, except for some innovation signal. And then this is posed as an iterative reconstruction problem, where the data consistency term is usually updated, followed by a regularization step. And it's an iterative reconstruction, so it's repeated some number of iterations until convergence, starting with some initial guess. And the data consistency takes explicitly our forward model, which includes the coil sensitivities and the sampling. Now, we could also represent this iterative reconstruction by representing each iteration as a separate block. And this is commonly done moving to the next step, just as a way of representing the same iterative algorithm, where we iteratively apply data consistency and regularization. And so this forms the backbone of all of these underdetermined inverse problems for MR in the before time. But in the last few years, model-based deep learning with MR reconstruction has really shown that this can be the best of both worlds. So we take elements from deep learning, but we still maintain this general iterative optimization approach. But instead of using a handcrafted regularization, we will replace the regularization with a deep neural network. And one of the works in particular, MODL, replaces this regularizer with an autoencoder. And so the autoencoder RW of X is a convolutional neural network with weights W. And its goal is to essentially denoise and de-alias the image X. And so if we do a good job, we expect this regularization component to be very small because the output image and its autoencoded version will both be clean and they'll have a small L2 norm. And so using this regularization, instead of the handcrafted ones, we can go into our iterative algorithm and start replacing components with convolutional neural networks. And now, instead of calling it an iterative reconstruction, we'll call it an unrolled reconstruction algorithm, where we're explicitly unrolling it for some number of iterations. Now, in the case of MODL, this data consistency term can be solved with a conjugate gradient algorithm, which itself is an iterative algorithm. And so this also will be unrolled in these types of approaches, leading to one big feed-forward network that combines optimization steps with deep learning steps. And these methods are usually trained with supervised training. And so we have some database of undersampled data, K-space, and here I have capital N of them. It goes through our unrolled reconstruction algorithm. And then we have our bucket of ground truth images that we're going to compare to. And so we have some loss metric that looks at the output of our reconstruction. And then we use that to update the weights of the neural network. Once we have the updated weights, we can plug them into our unrolled network, and we can take a new sample that comes in and pass it through this feed-forward approach. Now, this is a really powerful approach, but one of the drawbacks of this vanilla model-based deep learning is that it does require knowledge of the sensitivity maps. And these sensitivity maps have to be estimated from the data. And so any error in the sensitivity map estimation is going to propagate through the network. And whatever method we use to estimate them also takes some computation time as well. In addition, it's sensitive to acquisition parameters. And so here's a figure taken from a recent paper from PNAS 2019, where they compared a deep MRI reconstruction similar to this unrolled one that I showed that was trained at a particular subsampling rate, but then evaluated at different subsampling rates. And what they found is that as more and more data was available to the network, which you would expect it to do better in that case, it actually started performing worse over the whole training set. And so there's a real necessity to carefully matching the acquisition parameters at training time and at inference time. Now, we've tried to address some of these issues, and our work, which we call Deep JSense, tries to estimate the sensitivity maps and the image in a joint manner. And so the prior work reconstructs the image with predetermined sensitivity maps. And these sensitivity maps are either estimated through some type of deep learning method, which is something relatively new, or they're estimated with classical methods that come out of signal processing literature. And in our work, we jointly estimate the image in the maps by doing an additional unrolling of an alternating minimization. And this builds on this JSense algorithm, which is an approach in the MRI community for doing blind multi-channel deconvolution, but with a deep learning twist. Now, if we go back to our multi-coil MRI model and look at it in the frequency domain, we know that in the image domain, our unweighted image is multiplied by the sensitivity map of each channel. And then the data are Fourier transformed and sampled. But we can also represent this explicitly in the Fourier domain as a linear convolution, where we use the kernel of the sensitivity maps convolved with the kernel of the image, and then that is sampled to give us our data. And in particular, the sensitivity maps are smooth. And that means that they'll have a compact kernel in K-space. So they don't necessarily need to be represented by the full size K-space kernel. And so this motivates our unrolled alternating minimization, where given sample data from all of the coils, we want to solve this inverse problem that again consists of a data consistency term and regularization. But now we're optimizing over both variables, the sensitivity maps for each channel and the unweighted image in K-space. So this is directly in the Fourier domain. And we represent that as a linear convolution that's then sampled. So this A matrix just represents the sampling operator. We'll use deep learning for the regularizations, and we'll have a regularizer for both the image and for the sensitivity maps. And we'll explicitly represent the sensitivity maps with a compact K-space kernel because we want to explicitly impose the smoothness prior. And as a secondary benefit, it also reduces computation because we don't need to represent the image, the maps explicitly as a full-sized kernel. Now, one alternating update step, so the inner level of our algorithm looks like the following. So we have our data Y that comes in. We have our image at the jth iteration, and we have the maps at our jth iteration. And when we hold one of these fixed, because it's a bilinear problem, we still end up with a linear least squares. And so we use the conjugate gradient algorithm to update the sensitivity maps given a fixed image. These sensitivity maps are then passed through a convolutional neural network to refine them. And then we update the image using the same linear least squares model in K-space, and we perform conjugate gradient algorithm on the image to get an updated image. And we pass that through its own convolutional neural network to refine the image, to remove the aliased components. And so our networks are similar to MODL, where they're convolutional based. And then the entire system is unrolled and trained end to end with a supervised loss. And in this case, we're using structural similarity. Now, at the outer level, a question?
Yeah, I have a question. How do you initialize the sensitivity maps here?
That's a good question. I'd have to verify with my student because we checked a couple different options, but I think what we do is we'll just use a zero-filled K-space, and then we'll estimate the maps as the root sum of squares. So we'll just divide each coil image by its root sum of squares of the whole coil images, and that will give a really crude estimate of the sensitivity maps. But that relies only on the calibration region data, which I'll show a little bit later. And then the image is also similarly initialized with its zero-filled version.
Thanks.
Mm-hmm. Okay. And then at the outer level, we again see this iterative unrolling where we have an outer step that takes the initial maps and image, and then it's refined, and then we go through n of these iterations. And then we have a final inverse Fourier transform and combination into a single image, and then that's compared to a ground truth image fully sampled to give us our loss metric, which we then use to update the weights. And so we train this end to end with a supervised structural similarity loss. Now, for this particular work, we trained and evaluated this on the FastMRI me data. So FastMRI, which is a collaboration between Facebook and NYU, provides fully sampled data sets. And these have 15 coils and roughly 15 coils in each of these different scans. Now, just due to computation reasons, we didn't use the full training set. We used a subset of it, and we used about 4,500 slices for training and 950 slices for testing. And we implemented this directly in PyTorch. And we used BART for estimating sensitivity maps in the classical way. And we also used a really awesome package called SigPy to compare the alternating minimization of JSONs in the classical ways. Now for comparison, we compared to MODL, which was the unrolled network that only estimates the image given fixed maps. And we also compared to end-to-end VARNet, which is Facebook's Unrolled network that has a deep learning model for estimating the sensitivity maps. And so end-to-end VARNet is also an approach that doesn't require pre-computed sensitivity maps. And what they will do is they will first estimate the sensitivity maps with a convolutional neural network, and then pass those sensitivity maps to the rest of the Unrolled network, which would look very similar to MODL. Now, at test time, we also evaluated the effect of changing the number of measurements, as well as different calibration region sizes. So in classical methods, we typically fully sample the center of our data, and then that's going to be used to estimate the sensitivity maps. But because our method is estimating the sensitivity maps and refining them as part of the optimization, we don't explicitly need to have a large calibration region in order to get that one-shot estimate. Okay, so some results. R equals 4 means the acceleration factor. So this is 4 times accelerated compared to a fully sampled scan. And just at a high level, what we see is, in general, we get slightly better reconstruction performance when we iteratively refine the maps. And the estimated sensitivity maps have less leakage of image information, of image content, compared to the E2E VARNet, which estimates the maps as a single shot estimate and then doesn't refine them. And across the entire validation set, across the entire test set, we see that our metrics improve, which is just nice to see in general. Although in this work, we're mostly focused on the robustness question. And so let me zoom into these 2 different examples. So here is the ground truth image. Here's MODL, which is the Unrolled network that takes fixed maps as an input. And these maps were estimated with the eSpirit algorithm. End-to-end VARNet, which is the method that has a single shot update of the maps. And then our Unrolled JSense, which estimates the maps and refines them over time. So in particular, you can see that MODL, there's still some residual aliasing in the bone. And I would say that the relative differences between ours and end-to-end VARNet are marginal, although we do improve slightly on the metrics. But one thing you can see in particular is that their estimated maps here have leakage of the image content inside of them. So you can really see the outline of the bone in their sensitivity maps. And I'm only showing one sensitivity map. Keep in mind that there's 15 of them in each of these data sets. And if there's leakage...
John, sorry, stupid question, but for me to understand, how many sensitivity maps are there? Are there as many coils as sensitivity maps?
Yeah, that's a good question. There are as many coils as sensitivity maps. So each coil has this particular sensitivity profile. And so we can represent that as its sensitivity map.
So is it just again, I know it's a stupid question, but I'm just trying to understand what the sensitivity map is. Is the model that there is a real image and then every coil sees the real image times, like point-wise multiplied by the sensitivity map?
Yeah, exactly. So here's the model that we have and when you say real, we have to be careful. It's still complex value, but it's uniform sensitivity. So over the image space, it shouldn't be affected by any shading, right? The tissue in the top left of the brain, if we put you inside the scanner in the opposite direction, should stay the same intensity.
I see. So every sensitivity map has a real value for every pixel, not a complex value for every pixel.
No, the sensitivity maps are also complex value.
Oh, okay, so they can change the phase too.
Yeah, they can change the phase. And something I didn't mention, which is actually super important, is that the sensitivity maps will change based on the object that you put in the scanner. So if we scan you versus me, we'll get different sensitivity maps. Oh. And that means that we can't just estimate them one time and then fix them. We have to estimate them per subject and even sometimes per scan.
Oh, I see. So then we never have ground truth, or we never have even a sense of the ground truth for the sensitivity maps.
Right. The sensitivity maps, it's more of a model. It's a really good model, but we don't have a ground truth. Okay. So when I talk about this FastMRI data set, where we have 15 coils per scan, the data set itself doesn't have the sensitivity maps. It just has the coil images. Got
it. And what are these barcodes again?
Yeah, these barcodes are 1D sampling patterns. So in my cartoons, I was drawing it as these samples on a grid.
Right.
But we can also think of it as these are actually lines into the board. And if we looked at it at a different orientation, then these would just be lines that we're sampling. And the reason we're doing that in this case is that the FastMRI dataset is a 2D acquisition. And so the sampling pattern that we get is fully sampled vertical lines, and we can choose to skip however many of these vertical lines as we want.
Okay, and DC is in the middle. That's why you always observe the middle, because that's the most important stuff, right?
Right, DC is in the middle. So that's going to have most of the signal energy. But also, we typically sample a range, a calibration region around DC. And we use that to get a low resolution estimate that can be used for the sensitivity map estimation.
Thank you. Thank you. Thank you.
Hi, John. Can I ask you a quick question? So for all the training data and the underlying image of interest, do you require them coming from the same set of coil?
From the same set of coils? No, that's a really important question. And I don't know if that made it into my slides. One thing that, let me go back here. One thing that's really important to note is that this network here needs to be agnostic to the order of the sensitivities, right? If I permute the data, there's no order to which coil is coil number 1 and which coil is coil number 2. And so I don't want my network to memorize the ordering of the data. And in particular, I also don't want it to memorize the shading of the maps, right? If all of this data came from the same scanner with the same coil array, always scanning knees, it's true that the sensitivity maps will be different for each scan, but they will still be very similar to each other, because ultimately a coil placed in the top left of the knee is going to be sensitive to that region of the knee. So in order to handle that, we need to make this permutation invariant. And the way we've done it in this work is we put the coils in the batch dimension so that we're not actually explicitly taking advantage of all of the correlation among the maps, but instead we get away with this permutation invariance.
Yeah, thanks.
Yeah, if we didn't have the permutation invariance, what we've seen is that we'll actually start memorizing the coil maps. And so if you permute the order, the network will try to smooth out the maps to look like what it expects. So that's a really important distinction to make. Okay.
Hey, John, can I ask a question? Like, in order to compute your target or ground truth images, how do you compute the sensitivity maps?
Okay, so our supervision is only on the root sum of square image. It's only on the fully combined images. We're not explicitly imposing anything on the sensitivity maps.
Oh, okay, got it. Thanks.
Okay, other questions? All right, so I think we were here. Yeah, so the takeaway here, what I was saying is that end-to-end VARNet, which does estimate the sensitivity maps as part of its reconstruction, so it's also an unrolled network that can be viewed as a feed-forward deep learning network, but there is some leakage of the information content from the image into the maps. And so even though qualitatively it doesn't necessarily in this case lead to significant differences, it's important to understand that these variables are coupled, and you want to do your best to get the image content in the image and the sensitivity content in the sensitivity maps. And so our sensitivity maps don't reflect that kind of image leakage, at least not as much. And I'll also mention that we're not cherry picking any of these results. These are just arbitrarily chosen from the test set. And so here's another example of a different contrast, and we kind of see a similar trend where MODL, which uses estimated sensitivity maps pre-computed beforehand, it still has some residual aliasing that you can see. And so that's these lines that you see in the muscle that goes into the bone. The end-to-end VARNet, again, the sensitivity maps also has some of this structure that's still visible, whereas ours, which is explicitly represented by a compact kernel, so it will be smooth, but still has some refined features by the end. Okay, now we can also look at what happens out of distribution. So this is going back to the paper that looked at robustness of these different models. And here we vary the acceleration factor at inference time. So again, the model was trained with an acceleration factor of 4. That means that we threw away four times the data. And here is our method compared to MODL and end-to-end VARNet. And as we reduce the amount of, as we increase the amount of data we have, so as we go to lower accelerations, we see that we maintain this nice, almost linear performance, whereas end-to-end VARNet starts to decrease, which is consistent with the results of the robustness. And so some of these models are overfitting to the acceleration of the training. And what does that mean? It means that the particular acceleration factor is going to induce a certain type of artifact of undersampling, and it's overfitting to removing those kinds of artifacts. Now, because we're estimating the sensitivity maps as part of the unrolled network, we also don't explicitly need the calibration region in order to do that. And so here we evaluate our algorithm with different amounts of calibration data available. So the ACS size is the auto calibration region size, and it's the number of fully sampled lines around the DC component. And of course, as you get more and more of these lines, you have fewer lines that you can allocate to the high frequency samples for a fixed acceleration factor. So as we go to the right of the graph, this almost becomes a super resolution problem where we only have low frequency samples. And in particular, we're able to avoid this drop in performance as we remove the number of samples available for the calibration region. And again, that's because these other methods, even the ones that estimate the maps as a single shot estimate, are using the calibration data explicitly to do that. And so as the calibration data is reduced, their estimates are also reduced, also decrease in performance. Okay. Now, moving beyond MRI, we're really excited to apply this type of approach for general bilinear problems with this unrolled alternating minimization. So we've shown how this can be used for parallel multi-coil MRI reconstruction. And we're also interested in applying this to different instances of blind multi-channel deconvolution. And in particular, we're looking at this in wireless communications as well, where MIMO has a similar model for the channel and the data signal. Okay, so that was a big story about reconstruction. And I will just talk a little bit about acquisition, although this is still very much in the early steps. And so all the previous work I just showed is about reconstructing an image given limited measurements, right? But we started this by saying that we can vary the sequence parameters to generate the signal in the first place, before we acquire measurements. And the question is, what's the optimal way to generate that MR signal? What sequence parameters should we choose in order to get the best underlying image that we then sample? And a number of statistical approaches have been used really successfully. And a lot of them kind of work off of the idea of Kramer-Rao lower bound, which is related to error rates of unbiased estimators, and it's in a sense data agnostic. It's just using the statistical model to say we want to get the best performance of this particular statistical model where we have, say, Gaussian noise. But we could also take
just understand this setup. Are you adaptively selecting the next measurement? So it's like active learning now, where you're choosing the next point in k-space to observe?
No, so we're not doing an active learning. And I also want to emphasize that I'm not talking about just the sampling pattern itself, but actually the signal generation. And so this is all offline, and it's to say we want to make a particular signal that will then image. You could also frame this in an active learning setting, but that's not what we're doing in this case.
Okay.
Yeah. So if I go back to this slide, we can think of it like, what is the best configuration of these knobs in order to get a particular image contrast? But as I change the knobs, I'll get a different contrast. And so that's important to choose wisely.
Got it.
Yeah. Okay, and so the question is how to choose them wisely, and statistical arguments have been made with a lot of success. And nowadays we're moving to more of these data-driven approaches where we could just directly use the fitting error to evaluate the how good this set of sequence parameters are. Now, in both cases, though, we require an MRI simulator effectively if we're going to use this in an auto differentiation kind of framework. So we need it to be differentiable. And so we've been working on a massively parallel MRI simulation, also implemented in PyTorch and fully differentiable, that can simulate multiple spins in parallel on the GPU. And so here is an example, and we're using the extended phase graph algorithm to do this, where we start with a distribution of spins, like we said before. And then by playing particular sequence parameters, we can disturb or perturb the spin distribution. And in particular, we will choose RF pulses that will cause the spins to rotate. Then they will be subject to different off-resonance effects due to the physics of the MRI. And then they will also have their tissue parameters, theta, affect their components as they return back to the equilibrium state where the next MRI experiment would repeat. And so we've implemented this in parallel on the GPU, where we've implemented these different components of the extended phase graph simulation. And we've tried to do this in a way that's very easy to use so that you can simulate thousands or tens of thousands of spins, because ultimately we want to do this with spatial information. And we'll need to simulate many thousands of spins in one iteration of our update. And so here's a code snippet where, after setting up the particular variables, we can call our parallel extended phase graph algorithm, which can be differentiated with respect to the scan parameters, as well as with respect to the tissue parameters. Now, we've compared our simulation to naive simulators. And so these are all extended phase graph algorithm simulation frameworks. And this is looking at the batch size. So how many spins we simulate in parallel. And our parallel EPG on the GPU is essentially flat across this batch. So each of these simulations is actually quite cheap, right? It's just rotation matrices, of 3x3 rotation matrices, and some manipulation of those elements. And so that's why we're able to take advantage of this parallelization to really push the batch size up until we're essentially memory limited on the GPU. And if we just take this code and we try to do a similar thing, then we don't get this nice scaling with these other simulators. And so this is going to form the backbone of our simulation framework in order to then plug in the learning the scan parameters with the reconstruction. Now, one particular application, though, is we could combine the simulator with a fully connected neural network to estimate the tissue parameters themselves, and then optimize the sequence parameters to minimize this error. So here are the parameters of the particular sequence, the MRI sequence that's going to change the signal. It goes through our differentiable MRI simulator to give us the signal. And then we could plug that into a very simple signal decoder based on a fully connected network to estimate the tissue parameters. And because this is fully differentiable, we can then update with respect to the tissue parameters. Now, we can generalize this idea and say that in general, if we have some tissue model, theta, and so those are the parameters of each of the tissue, each of the spins in 3D space, and we have our scan parameters u, then we can simulate them using our EPG algorithm to get a signal x. And then we could ask the question, can we estimate from the signal x, can we form an estimator t to estimate the tissue parameters theta hat? And this estimator could be a deep neural network, but it could also be conventional methods like non-linear least squares. But the key takeaway here is that whatever method we're using to estimate the tissue parameters, if it's differentiable, then we can use it in this setting where now we minimize over the scan parameters to try to reduce the error between our tissue estimate and the true tissue parameters. And so then we can update the scan parameters given this particular reconstruction. And this reconstruction itself is an unrolled neural network, an unrolled network consisting of both model-based components and deep learning-based components. Okay, so that's all in the abstract. It's still work in progress. And so kind of the next steps there are to combine the differentiable simulator with a deep learning recon with our unrolled JSense. And I just recently, this paper came out that I think is really exciting and really captures the essence of this area. They call it MR0, which is essentially attempting to discover the best sequence using the supervised learning framework. So they have the simulation and reconstruction implemented that's differentiable, and then they can pass that through the simulation to get a particular contrast and then evaluate this in order to find the best scan parameters or potentially the best reconstruction as well. And so this is the direction that we're taking this work, combining it with our unrolled reconstructions. All right, any questions? Okay, so I'll start wrapping up, maybe a little bit early, but I just want to say a word of caution. So if we zoom in on this really nice image reconstruction, we might see something that we're not quite expecting. And as we move to the era of big data, we need to be cognizant of small crimes. And in particular, when we're working with MR, we need to concern ourselves with subtle inverse crimes, where the use of all of these big data training sets to solve inverse problems can often lead to overly optimistic results because we're not necessarily exposed to all of the pre-processing that these data sets have gone through. So when we download our data sets from the cloud and we don't know how that data was pre-processed, and then we just use it as a black box for our reconstruction, then the results we get might not translate to the clinic. And so this is really great work by my colleague Efrat Shimron that I recommend checking out at ISMRM coming up later this month. Okay, so with that, I will conclude. And I would like to thank you all for your attention and happy to take questions. Thank you.
Great job, John. So let's open the floor for questions.
Hi, John. I may have a question regarding your last project. Talk about that. So I see you use SSIM as your loss function. Have you tried the multi-scale SSIM plus L1 loss? Because I think that is more reasonable loss to me. Have you tried ever before?
Okay, so the question is, what's the best loss metric? And this is really an open problem. We're using SSIM, you can tell that this table was cropped. So we also have other metrics to show, other quantitative metrics, and we're improving on all of them. But the quantitative metrics somewhat miss the story. And ultimately, we need to see how they perform under a diagnostic setting. Now, you could tune it a little bit, and you could add an L1 loss as well to the SSIM. That's something that's done in practice, but we just kept it simple. So I believe that the trends will follow a similar path if you change the loss functions a little bit like that. But in this particular case, we only used SSIM for training.
Yeah, thank you. And so when you train the models, how do you deal with background loss?
How do we deal with background noise?
Yeah.
I'm not exactly sure if I understand the question, but there's two sets of background noise. This is just a scan, this image, the ground truth. So it itself might have background noise. And it's a question of, do we really want to call that the ground truth? So that's maybe background noise that you mean, but then there's also maybe you mean the background noise of our reconstruction. So
I mean the ground truth.
Yeah, that's a good question. So we're not explicitly dealing with that, but we're going to hope that by seeing enough training samples, that kind of effect gets averaged away. Now, but there is a good point there that I also want to bring to your attention is that, and this is just an artifact of the way that we do our supervised training, because our supervised training is on this ground truth image, and this ground truth image has noise outside of the field of view, then actually our image reconstruction is going to be penalized if we set the background pixels to 0. So we'll get an artificially worse performance, even though the image hasn't actually changed. And so that's why you can see in all of these sensitivity maps, we explicitly allow for non-zero components outside of the field of view so that we don't artificially hurt the quantitative metrics. But in practice, it's not actually providing any value to the image reconstruction. And in particular, we could reduce the noise of our reconstruction if we explicitly set those background pixels to 0, but we won't get a good quantitative metric on these open public data sets. So that's one reason that we don't do that.
Yeah, Thank you. Thanks for your great talk.
Thank you.
Great. Any other questions for John?
Hey, John, I'm just curious, this end-to-end learning paradigm, which includes the acquisition parameters, what are some of the biggest technical hurdles with that? I mean, the whole decoder structure is pretty, well studied, but the encoder part of it and linking that with the actual parameters itself, I'm curious kind of where that field is headed.
Yeah, that's a great question. So it's true that most of the work has been done on the decoder, because I think that fits in really well with standard inverse problems. But I will mention that a lot of work has been done on encoders, on the acquisition parameters, but using classical methods, using statistical methods typically, or using heuristics that are handcrafted. And I think that now the biggest challenge is making this computationally feasible and tractable, because what we're doing right now is we're simulating the sequence with really simple and assumptions. And so it ends up being computationally simple. But as we move to real acquisitions where we want to simulate a 2D image, we're now simulating for each voxel multiple spins. And this just takes a lot of computation. And it's also not clear how easy the differentiation is, right? It's a heavily nonlinear landscape. But I would really recommend checking out this paper that talks a little bit about some of these challenges. So in particular, the training time for these is very expensive because one outer loop of this training algorithm can take 30 minutes.
Great, thank you.
Thanks. I see. Yeah, this is opening. And I guess going back to my question, is anybody considering active learning approaches where you are adapting your case-based measurements? Yeah, and there have been some active learning, in the before time and now as well. So nowadays, there have been a few different works that use reinforcement learning to try to pick the next sample. So that's generally the way it's done, whereas previously it was done in more of these greedy methods where using a training set, we see which sample would best minimize the training error and then try to generalize that on the next set. Right. I see. I don't think that with those works, to be honest, it's not clear to me if it's actually improved over having a fixed sampling yet. Although one thing to note is that everything we're doing right now is in the simplest possible setting where we have 2D images and we're choosing essentially out of 256 numbers, let's choose a subset of them, right? Which integers to sample. And the MR system is way more complicated than that, right? This image that I started with, which is this nice dynamic imaging experiment, is way more complicated than that 2D setting. And so I think there's a lot of room to learn better acquisition and better active sampling in a setting like this, especially when we start talking about artifacts like motion. Yeah. And John, another kind of related thing is to the computational bottlenecks. I know FastMRI is quite low resolution in the 300 by 300 pixel range, right? So are these diagnostically useful images, or the diagnostically useful ones have to get in 1000 by 1000 or higher res? No, actually in MR, that's pretty typical. So that 320 by 320 or 380 by 380, that's the matrix size, and the corresponding resolution for those 2D scans is usually something like 0.5 millimeter. With 3D scans, it's not as high resolution, and those are still diagnostic, but they're kind of on the limit. 1 millimeter is really the largest you can have for lots of pathology if you want to be able to detect it. But it always depends on what the particular task is. Okay. But there's almost never 1000 by 1000 MR image used for diagnosis, at least not at acquisition time. Is that because the computation is a problem, or or we don't have enough measurements, or what's the problem, or it wouldn't be even useful? No, it could be useful in moving to higher field. So really, the issue is always it's a scan time versus SNR versus resolution trade-off. And so if we can boost the SNR, we could potentially have a higher resolution. And so moving to higher field, that's one way to get higher resolution.
If we use these models that let us reduce scan time and trade it off for resolution, we can do that. But resolution is really expensive. The SNR and resolution are inversely proportional. So that's really the bottleneck. If we want to move to 0.25 millimeter resolution isotropic, then we're essentially going to have a 60 times longer scan.
I see. And nobody has ever done those scans to produce very high resolution images?
People have done that in vivo with high field MR, and they've done it ex vivo on tissue samples to get really high resolution, for instance, looking at tractography of the brain. But it's not typically done clinically. Since I have the floor and we have 15 seconds left, I'll say that even in the case of knee imaging, it's not clear that you really need that high resolution. I saw a really nice study that accelerated the scan by lowering the resolution, having a worse resolution. And so you also want to make sure that you're matching to the actual task and making sure that it's useful. The places where high resolution is really used nicely is for neuroimaging experiments where they're really trying to map the brain, like the Connectome project.
I see. Very good. Thank you very much. Okay, so just as a last comment, our next ML+X seminar is in 2 weeks, and it is by George Biros. I just want to remind everyone to continue coming to the series. Thank you very much, John, for a great, very informative seminar, and see you all in 2 weeks. Bye-bye.